While using the XGBoost would not require you to know anything other than the way you have been doing, right? So the only thing probably you will have to take a look at is how to tweak this parameter, that parameter, and that's all hyperparameter tuning. Okay. What was needed for the XGBoost, it was the understanding of XGBoost, and that's what we were going through last time towards the end. All right. Okay, so we all know that in the supervised learning, we tweak the weights. Then the thing was that there are two parts to it. The loss function, there are two things we optimize. One is we minimize the error. Second, we regularize, right? These are the things that we do. Regularization makes sure that our model remains simple while bringing down the loss basically does the training. Right. So what happens in case of XGBoost is that as you add a leaf or as you create trees, right, while on one hand, the training loss is going to come down, right? On the other hand, this is going to go up. This is coming down, this is going to go up, right? Now, that's the fine balance. I mean, as you are adding more leaves, this is going up, this part, because this error, this regularization is basically, it starts to overfit as we add the leaves. While this comes down, that's a good news, but this is a bad news when we add a new leaf, right? So what we do in this case is that what Tianqi Chen figured out was that as we add new leaves here, so there is X amount of increase here and there is X amount of decrease here, let's say, right? Now, what is that fine balance and how do we generally find that fine balance of adding a new leaf, right? And that fine balance was done using a simple differential calculus thing, right? And those who are aware of differential calculus, they would know that let's say we got y in terms of x, so we can differentiate this objective function in terms of leaf and in terms of leaves, and we can figure out that what is that fine balance, right? That's what is happening here. So, right? So that's what is happening here. So let me go ahead. So basically, this is the objective function, this is the loss, and this is the regularization. Now, since it's an additive learning, it's a boosting because the loss at yth step is previous plus new one. Okay. Now, moving ahead. So now we basically broke it down into at every round whenever we are adding a tree. So note that here we are adding a new tree. Okay. So when we add a new tree, what happens is that the Y prediction improves a little bit or becomes bad. Initially, the Y prediction, when there is no tree, the prediction is 0. Then as we add a tree, the prediction is previous plus new additive value, right? And that's how we keep on going. At every point of time, the loss is going to be yi and y, the actual versus the predicted values comparison. Here L could be anything. That is one thing that they have done. But if you think about just mean square error, it's going to be this value minus the actual value and the whole square, right? So this is what's going on here. Right, this is the loss function, and loss function means that here it's saying that the loss, as in the mean square error between the step at tth step is equal to the loss of the previous step plus the improvements done because of this new tree, right? That's what it means, that, right? And as we go ahead, so if you just break it down into a square, and we will get a better results here instead of this putting all of that. So if the if you put the square loss, it's going to be loss between this and the whole square, right? So this was the actual value, and this was the predicted value in the previous step, and this is the addition that has happened due to adding a new tree at the tth step, right? So basically we subtract the two, we square the two, and then we basically expand it. So yi minus yi t minus 1 whole square plus ft x whole square, right? That's what is happening. And here this term, the whole square of this one, has been ignored. Okay, they put the bracket, remove the bracket from here, put the bracket here, right? And then squared it. Correct. Now moving ahead, and that's what is here, that's what's going on here basically. So at the end of it, the objective function is summation of 1 to n all of the trees, right? 1 to n all of the trees. And right, so no, this 1 to n is total number of leaves, and then this is sigma. Okay, moving ahead, that's what is happening here. And okay, now instead of doing it only for mean square error, what they have done is he has basically done it for all kinds of functions, right? And he has utilized something called Taylor's expansion. Those who don't know, they take a look. It's a wonderful expansion. So function f of something is equal to function f of something plus little bit. If you increase a little bit, it becomes fx plus, so the value of function f at x plus delta x is f of x plus f dash x, first derivative of x, then delta x plus second derivative of x by 2, x squared, and so on. So this is a very interesting function called Taylor's expansion. You can actually, let's say if you want to do sine x, right? So sine of, if you put, let's say initial x is 0, so you'll say, okay, sine of delta x equals sine of 0 plus first derivative, which is cos of 0, and so on. So you can actually generate any kind of expansion, even let's say for e to the power delta x, right? So you can actually generate the whole of, I mean, there are, of course, there are like infinite, it's an infinite series. The next is going to be f triple dash, meaning third derivative divided by 3, delta x cube, and so on. So this Taylor expansion is a very, it's basically done somewhere in 1800s, and it's very, very useful and very interesting part. And if you look at the definition of, first derivative, right, this is exactly this. Okay, think about how do we calculate the first derivative. It's basically we increase a little bit x and subtract by the x value, the function value at x, and divide by delta x, right? If you just think about this portion, so it's essentially defining the first derivative of f, right? So and the second derivative is defined like that, and that's how this Taylor series is. Okay, so it sounds like crazy that first we use compute the first derivative using this formula, and now we're using this for, right? So it's very, very common to use these things. So anyway, even if you don't think about Taylor series for a moment, not at all, what you do is just use, instead of loss, you just put mean square error, and then you'll get the answer. Now basically right, this is not, if you're not comfortable, you can always think about it like you know, mean square error. So you don't need it in order to generalize this function, so that in your case you don't have a function, which is, you don't have a function, you want to use some other performance measure instead of mean square error, the loss function. In that case, you can use this. I mean, it can generalize very well. Now, if you're not comfortable with this, so you can just think of it like, okay, here the first derivative of loss function at t minus 1, what's going to be? The first derivative of yt minus 1 is, and this is a whole square, mean square error. Its first derivative is going to be how much? 2 of this, correct? And the second derivative is going to be how much of your mean square error? Is going to be the derivative of this one, which is 2, correct? So essentially the gist is that we are defining two variables, g and h. G represents first derivative of your loss function, while h represents the second derivative of your function. Okay, and when you look at it, so it becomes like the objective function is equal to 1 to n, where I is going from 1 to n. The loss function, which is mean square error in the previous step. This was the mean square error in the previous step, plus the first derivative of loss function multiplied by the function value here, plus and so on. And this is a square of the loss function. Okay. Now let's go ahead. So this is the new goal that we got now to optimize. Okay. If you remove all the constants and so on, this is the new goal. And here what's happening is that, right, it is in terms of where I is going from 1 to n, which is the number of trees so far. Okay. No, this is number of instances. Yeah. Great. Now, what is done here is that the regularization function that we saw as just a symbol, the regularization function was again expressed as this, right? And what does it mean? It means that if you increase the number of trees, it will start to overfit, right? That means regularization function is linearly dependent on number of leaves, right? Second, we are adding one more thing called weights. Remember the ridge and lasso? That's what we are doing. So regularization term is having one factor as number of leaves and other factor as the weights. So due to increase in the leaves, the two things are increasing. Number one, the number of leaves are due to adding a new tree, due to growing a new tree. Two things are impacting our outcome in terms of regularization. One is number of leaves. As number of leaves grow, it starts to overfit. We know that. Similarly, as the weights grow, we want to regularize the weights, right? So we are putting one more part to the regularization called the summation of the weights. Okay, and we're going over for every tree, the tth tree. What we're doing is we go over all the leaves. We go over all the leaves from 1 to t, and what we do is we basically square the weights. Okay, like let's say these are the weights, so we square and sum it up. Right now, this is the final objective that we got here. This is the final objective, and we are saying that from 1 to n, this is what it is, and this is from 1 to all the leaves. Okay, so here you could always reorganize it. You always reorganize it, because if you convert it into 1 to t, as in instead of going over every node, right? What you do is you instead of going over all the trees and all the leaves, so what you do is you go over all the leaves, and inside each leaves you can sum up these things. That's what has happened. So this sigma became this, right? This sigma was broken down into this. So this is basically for each leaf, right? The weights are for each leaf, and so on. And when you have everything for each leaf, you can bring down all the terms that are summed over each leaf are these, meaning for each leaf compute this and then sum up that again for each leaf, right? And then there are, right? Now this is where it gets interesting. Once you have defined your objective function in terms of leaves, right? That for each leaf, this is what we're going to sum up, and there are the leaves here. So as leaf increase, while the prediction are going to decrease, right? Due to leaves, there is a declaration. That's where the main work comes into play. That in case, in case, let's say your function is this. Let's say your function is gx plus half x square, and you want to minimize this, right? So what do? Let's say you have to, let's say this is your function, which is having x minus x square, right? What is the minimum value of this one? Anybody? What is the minimum value, or what is the value of x where y is minimum? Okay, thank you, I'll say it. So yes, so we say this by this equals to 0, and which is the derivative of x is how much? Yes, 1, and the derivative of this one is 2x, right? And therefore x is 1 by 2, right? Now, in the similar way, if your function is gx plus half of hx square, what is the minimum value? What is the value of x for which we will get the minimum value? So we'll say this by this equals 0, and which is g plus hx equals 0. Therefore, x equals minus d by h. Correct? So that's what is mentioned here, that what is the value of x for which the value of this is minimum, which is minus g by h. Okay, this was one part that wasn't clear here, and therefore the minimum value will be when you put back x as this, which is going to be minus of g squared by 2h. Okay, so all right, so this is where we are right now, and this g is actually representing the first derivative and of our loss function. So and so on. So here we are, that in case we want to differentiate, so this function, this loss function, if we have to minimize, right? If we have to minimize this, the minimum value of this is going to be half of g squared by h, half of g squared by h, and which is basically what? This is g, and this is h, right? So half of square of this and plus okay, I think this is what is going to be, right? So he has defined here the various arguments. Let me just move ahead a bit. All right, so essentially this is okay, here we are just reorganizing it in terms of t. Okay, now is this part. So this is g, this is half of h plus lambda, and so the objective function is going to be half of g square by hi plus lambda, right? That's what we discussed here, right? So whatever is here, that comes down, and g squared. So the objective function is essentially essentially this. And now we have found out that, okay, for each leaf, what we have to do is we have to define this way. Now, our objective function now is half of summation over 1 to t, that is the total number of leaves, and this one. Okay, this again, this is the summation of all the first derivatives. This is the summation of all the second derivatives, and so on. Second derivatives of your loss over all the what do you say, in each of the leaves, whatever element, whatever values are there, whatever instances are there. If you, so this g is essentially the loss, the mean square error, the first derivative of mean square error in each of the summation of the mean square, first derivative of mean square error inside each of the leaf. That's what it is. Okay. So this is summation of gi, right? From on all of that, on all of the instances in a leaf, correct? Here we are going over each of the leaf. In each of the leaf there will be instances, and this is the summation of gi. Gi was what? Gi was basically the first derivative of a loss function. And so what we're doing is, let's say our mean square error is x, that there is a mean square error. The first derivative is going to be twice of the x1 minus x2. And so what we do is we compute the loss, the first derivative of the loss inside each leaf. That's what is capital G, right? And here the h is the second derivative of loss and the value of it inside each of the leaves. Okay, so we got G and H, and this is the main one. And what we do is now, as we add a tree, we figure out that, okay, that this objective function is going down or going up, right? So basically at every point of time, every point of time, what we do is we basically optimize this. Okay, so calculate the structure score Q using the scoring equation, this. Okay, so what we do is enumerate the possible tree structures, right? So what we do is we figure out or come up with new tree and add that and see if this objective function is going down or going up, and so on, right? And this is the optimal weight of the leaf, right? And so on. So yeah, so at every point of time, whenever we are adding, or whenever we are adding a tree, or when we are creating a new tree, right? So we could basically optimize upon the gain. This is the net gain. Similarly, at every point of time where we are trying to add, I mean, even we can remove a tree and then again compute the objective function and so on. So for each leaf node of the tree, we try to add a split. The change of the objective function because of this is going to be here, and so on, right? This is the score of the left, the score of the right, and then that's what we came up with, this the objective function, right? And because we are adding a one leaf, therefore number of leaves going to be added is 1. So t is previous, let's say t1 minus t2 is going to be 1. That's what it is here. Okay, so if we are introducing an additional leaf, the difference in overall objective is going to be this, and this is the gain which we need to compute on every split. Okay, this is the gain on every split. All right, so that's what is happening here. So at every point of time, what we do is we try to split and then compute this loss. This is the loss of right, this is the loss of right, this is the loss of left, and that's what we compute. Okay, and how do we compute the loss? Let's say we are splitting it here. We compute the mean square error in this weight, and as well as then second derivative is the first derivative of mean square error on both the leaves, both the values here, 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 and we sum them up, and that becomes our capital G. Okay, and if you sum up the second derivatives of the loss, right, that becomes our capital G, capital H, and that's what is happening. Okay, now so you can notice that the linear scan basically whatever we were doing in case of normal decision tree, whereby we take a node, split it, and then take another node, then split it, and the similar model goes on over and over, right? So this is what happens in case of the XGBoost also, that we, for each node, we enumerate all the features, and for each feature, sort the instances by feature value, right? Use the linear scan to decide best split along the feature, and take the best split solution along all features, right? And the complexity is similar, and so on. All right, so that's what is happening. And also there is something called pruning. We can also do the pruning, as in we can delete a particular node if the gain is not there, right? Okay, so this was a quick intro. Those who are interested, they can take a look at this presentation, as well as these are the two good resources, this one and this one, okay, for the presentation of this one. I was thinking of making it simplified, but that did not happen. All right, so let me just give you one more. There was one part that I had to explain. Okay, this one. This one, Gonzalo, or okay. Okay, okay. So what I'll do is I'll put them separately, because there is a lot of unnecessary slides here. So I'll just put them separately, and let me put it. Let me note it. Okay, okay, sure. Sure. What I'll do is I'll basically separate them, which part I can share, and then, okay. All right. So all right. Okay. So here, so in case of XGBoost, again, it's basically parameter tuning is very dark art, because there is no right or wrong way, right? So it's impossible to create a comprehensive guide to do so. It's just important to understand the bias variance trade-off, which we all know, that on one hand, when the model is too simple, it's biased. If it's if the moment we try to make complicated models, there is a huge variance, right? Now, a simple model does the underfitting. It basically has a less ability to fit the data, while on the variance side, it has the better ability to fit the data, but it can overfit. The simple model will fit bad on the training as well as test, while the complex model having overfitting will perform good on training but not on test. Okay, that we all know very well. So basically there are these all kinds of functions like the max depth. Max depth, we all know how many depth can we go to, minimum child weight, right? And then gamma, I remember that gamma into capital T, it will basically what is the coefficient with which we should multiply number of leaves in order to regularize. Bigger the gamma, more is the regularization. Okay, and okay, so use randomness to make training robust to noise, and this includes subsample and so on. So just take my simple suggestion to you will be just take a look at the parameters of XGBoost, and there are a couple of parameters which are known to work for quite a few Kaglers. So you can just pick up their parameters and start from there. Okay, so I mean, some of the Kaglers have found a really good combination of XGBoost. I think I've mentioned it somewhere. Let me. Okay, so one is general parameters, right? And then, okay, so we can categorize the parameters into 3 parts: general, booster, and learning tasks. And okay, so this is all okay. Also, please note that XGBoost, as per the implementation, is extremely well done, because XGBoost has a version which runs on top of yarn, meaning distributed way, as well as it can utilize the GPU, as well as it can utilize the multi-core. Okay, so the library is very well done, and it's not part of scikit-learn. You have to install it separately. Okay. Okay. Right. So generally we use one of the parameters is booster. Booster means that this is for tree-based models, and right. One of the parameters is booster. It has 2 values called GB tree and GB linear, and we generally focus on the GB linear because that's a tree-based model. Other one is a linear model, and linear model is not really growing. It is basically, I'm not sure what it does. As far as I knew that it was supposed to be the tree. Never mind. So we'll take a look into the GB linear. Then the silent, instead of showing too many error messages, you can just turn on the silent. Okay. Otherwise, it will show you lots of logs. In case you want to understand the logs, then you can keep the silent at 0. Okay. Number of threads, how many? If you have multi-cores, you can utilize all of them. Okay. By default, it uses all of the threads. So learning rate makes the model more robust by shrinking the weights at each steps. This is the learning rate. And the minimum child weight is till what leaf do you want to go to and to tweak. So define the sum of the weights of all the observations requires in a child. So basically, minimum child weight, as in minimum child weight represents that what is the minimum weight in each of the leaf that we can go to, after which is we stop the further splitting. Okay. Gamma is basically if you have bigger gamma, more regularization, and will have less number of leaves. Okay. Max delta step. In max delta step, we allow each tree's weight estimation to be if the value is set to 0 and so on. Okay. So there are quite a few parameters. Just try to tune them, and you'll get the idea. Here I've mentioned something as we go ahead. Yes. So, right. So this is one of the ones that worked out pretty well. Okay. And here you go. All right. So this is one of the parameters, one of the set of the parameters that seems to work for some, but you are free to try out more permutations of this. That's why we are using the grid cells. All right, to learn more, you can go here. So let's just see the notebook. Okay, so in my opinion, there is no single way to decide which parameters should be kept how much. But you can start with these kind of parameters that others have experimented with, and that seems to work for many. Okay. And let me just open my notebook. All right. A question from Robert is it better to use XGBoost as a standalone classifier or within an ensemble? Generally, people use XGBoost as standalone because internally it's doing all kinds of ensembling already by adding more and more trees and so on. Question from Deepak is, does SparkLib has XGBoost? I don't think so. I don't think so. The XGBoost is separate from SparkLib. So though there is a one, but it basically would be making it available as like importable, external actually. Yeah, that's what I'm talking about, MLlib. I don't think the Spark has the implementation for XGBoost. So what is Spark? Those who are wondering what is Spark, basically Spark is a way to distribute computing just like Hadoop MapReduce, and it's really fast. So a lot of people have written a lot of machine learning things that we are learning as part of scikit-learn. A lot of people have moved most of these to Spark as well. The API of Spark MLlib is similar to scikit-learn, just that it runs on the cluster. All right. Okay. Okay, so it also, there's something called OpenMP. OpenMP is another way of parallelizing your task. In case you're planning to parallelize things, you can also use OpenMP, and it works very well on OpenMP. Looks like they have made a Spark API available. So though the package is not there in either scikit-learn or MLlib, the package is to be made available from outside. Okay, so you can take a look at that. All right, so that's pretty much about it. Let's just run it once. Okay, so here we are basically, you can see that NumPy XGBoost classifier, we are fetching the MNIST data, and here we are picking X and Y, and you can see that, and then we basically shuffling it, basically only creating a shuffled index out of 70,000 numbers. And using that shuffled index, we are shuffling X and Y. And after shuffling the X and Y manually, we are splitting it. Of course, we could just use scikit-learn way of splitting. And yes. So here, this is where we are running. It's just a classifier. We are saying xgbc.fit, and everything looks exactly like the way we have. All right, it might take a bit of time, so. All right, so overall, the accuracy of XGBoost was this much as we ran last time. And it was around 92%. All right, as you'll see in the coming chapters in TensorFlow and deep learning, we'll take this accuracy to 99.8%, 99.7 something percent. All right, and yes. So we started with 84. Okay, and now we are here. All right. Okay, the training is still going on. Yes, it is done. Okay. A question from Alcia is that I tried new data to classify, but it always gives me error about the shape of arrays. Is there certain shape we should adjust our inputs to classifier? No, but in general, the common mistake, as in the common way, is that your X has to be of 2 dimension. Okay, this can have any number of features, while this, let's say these are the number of instances, and okay, and this is Y. It can have again many number of labels, but this number of rows have to be M. So generally when you say the shape X dot shape, it should tell you that the shape of X should be M by N, and the shape of Y should be M by 1. Okay, so when you are checking and it's throwing an error, just check that, let's say here, this way we were running, right, X train. So X underscore train dot shape, you can see the number of instances are 5,000, and the columns are 784. right? Here it's, wasn't it supposed to be, here we've just picked up a small set. Okay, so make sure that you have this kind of shape. And right, like 0th element here in X is this. Okay, so what you notice is that this Y is a single column here. Okay, that's also acceptable. So this Y could be just a single dimension array, and X could be two dimension. Okay, so sometimes what ends up happening is, let's say X only has one column, right? In that case, you'll just create a single dimension and you would feed it, and that's where the error would occur. Okay, in that case, try to make it convert a single dimension to multiple column, and that numpy part, just take a quick look at the numpy. How did we do it? There was 2-3 such instances where we did that. All right. Okay. Instead of training it, we did not. Okay, so accuracy is this much, even though we trained only on 5,000 records. Even though we just trained it on 5,000 records, okay, instead of training on the whole data set, we trained it only on 5,000 records. Where is the Y predict? You see Y predict anywhere? And where did it go? Here, X test. Okay. Yeah. Okay. So yes, if you just train it on, like, let's say, will it ever finish? It'll take a long time. Never mind. So probably run it with this data set. Instead of 60,000, we had just run on 5,000 records. So in the same way, I'll say that you try to train it on this data set, right? And in your own time. All right, otherwise it will not finish right now. So even on 5,000 records, it actually works pretty well and give us close to 90. Okay. And in case you're trying to further optimize, you can try the grid search and so on. So it'll train this classifier so many times and compare the results across using the cross validation. Okay. Now, those who are not comfortable with scikit-learn, so, and they want specific API of XGBoost, you can take a look at their API, and they also provide a little different API. Okay, so though it has a train and a predict and so on. And oh, is this still going on? All right, so try out this, you can try it out and take a look. That's pretty much. Okay, so get started now, closing it and let it finish, and we'll continue our discussion. Okay, so these are the document that really liked, which okay. All right. Yes, Deepak, yes. Okay, he's talking about the reshape. Yes. So yes, we could use the reshape in case we want to convert two-dimensional into one dimension and so on. And all right, so XGBoost is generally a little more involving to look at the code. Probably not many people understand how XGBoost work, but they really well use the XGBoost. Okay, so even if you don't understand the internals of it, you can just use it like a black box. Okay, without having to worry what's going inside, you can just use it as is. Okay, even if none of the things that we discussed earlier is clear to you, still you'll be able to efficiently use it. All right, wonderful. So great. Shall we start with our dimensionality reduction? All right, so wonderful. So far we learned the various techniques. Some were primary techniques such as SVM, linear regression, and the decision trees. And the core of the entire game was gradient descent. Gradient descent was used in linear regression, though SVM has its own technique and trees have their own techniques. So gradient descent is something that is used in a number of ways. Okay, just like if we have the data ordered and we want to find out a particular value in that data, we can just do binary search, right? In the same way, if we don't have any clue about our order of the data, or if the data is sorted or not sorted, and so on, all we know is that we can find out the rate of change of output from the rate of change of input. If we can find out the rate of change of output from the input, we can change our input quickly to maximize the output, right? That's what is gradient descent. Any black box, if we can, let me explain. This is something you will notice again and again. Okay, let's say this is our black box, a machine given to us, and it gives us some value, and we put some value inside, right? Now, what we want to find out is that, right? Or how should I say? Okay. So if we have y, we have x, and we have some knob here, okay, that we can tweak. So as long as we can, find out the impact of rate of change, okay, as long as we can find out the rate of change, okay, not x, I'm sorry. Let's say this is our x, this is something else, okay. All right, so let's say this is our, okay, so there's some input coming and this is giving something, right? And this is our let's say knob, this is input. So let's say we have to find out the knob or this point. As long as we can check how changing x changes y, as long as we can figure out how changing x impacts y, we can quickly change X in order to maximize Y, in order to come up with that Y, which is the best for us, right? If we know this, right? So if we basically can tweak X in some way, okay? So basically, if we can observe the impact in terms of rate of change, if we can do that, then we can apply the gradient descent to do the predictions, to quickly optimize X, quickly optimize that input. And other techniques for similar things are like binary search, which we have done earlier, but that's only possible if we know for sure that our output data is sorted. The other thing you can think of is, let's say, a hash table, right? In a hash table, given a X, you always predict Y, but a hash table cannot predict the value which it has not seen in past. So a hash table is a very good example or very bad example, in the sense that hash table has a perfect overfitting, but it is not capable of doing the predictions which it has not seen. Okay. All right, so we talked about the gradient descent, which used with regression and adding the features, and similarly, then we talked about SVM, which uses geometry along with linear regression, along with linear algebra, in order to find that plane that fits that separates the data well. Then third was decision trees, whereby we go over and over the features, figure out how to split such that the features are well separated. Now, these are the three primary techniques so far we have used. The fourth meta technique, we call it meta technique. Fourth topic was the ensemble learning. That was a meta technique, in the sense that ensemble learning can be applied to anything. Okay. It can be applied to anything, and inside ensemble learning, we first understood the trees, then we learned how to create the tree, we understood the CART algorithm, and afterwards we learned how to ensemble the trees, and we learned the importance of ensembling, that the ensemble's output is better than the best, right? And better than the best ensembled discriminators or ensemble predictors. And then we learned the other technique like boosting, whereby the things are, whereby the trees can be sequentially arranged in order to boost the predictions. And then we learned about the things like, before that we learned about random forest and other parts, which were ensembling techniques, in which we ensemble lots of decision trees and get the outcome. Now, then in the last we learned XGBoost. XGBoost is basically gradient boosting technique, and it's not really that. It's a little different from the rest, in the sense that we do not just arrange the trees, instead we grow the trees. Okay, so in case of gradient boosted trees, one thing that was different was that the objective function which we optimize, let's say in case of decision trees, we had a simple objective function. In case of the XGBoost, the objective function was highly optimized. Okay, objective function itself included the regularization term. So that was what we've learned so far. Bye bye. Have a good day.